Okay, so for tutorial 6 or tutorial 1, if you like reset your counter after switching to team duty. Okay, so this is like contextually very like kind of condensed matter heavy, but the actual maths could be the same. So if you have any like kind of background problems, better ask Tim because I'm not a condensed matter physics student. But yeah, the key point for this question 1, well, let me see, where on the board can I write up to? Up to here. On the other side. All right, so question 1 does some kind of like quantum qubit, quantum dot business. So you have some energy. Question 1. You have some energy EC that's defined as like your charge divided by 2 times some capacitance, some total capacitance. And then you set up some pretty cool stuff that I don't really understand, but at the end of the day, you get told that the energy levels in the system given by E sub n is 4 times this charge energy times the energy level n that you care about minus some n ground state, or sorry, n gate squared. So this ng is like a gate voltage, and it's defined as the capacitance of the gate times, I guess, the actual physical voltage of the gate divided by 2e. So the dimensionless gate voltage. And okay, and the ground state, this is the energy state of like the end state, but the actual ground state depends on like where you are in this like gate voltage parameter. So for example, if you're between -0.5 and 0.5, then n equals 0 corresponds to the ground state. Whereas if you're between 0.5 and 3/2, sorry, n equals 0. I don't know why I wrote 1. N equals 1 is the ground state. So as you move to higher gate voltage, your ground state energy kind of like increments up as well. So in reality, the point of this problem is that your gate voltage has 2 components. So you have one that's like actually set by you, so you set this. And then you have some other part that's just like a random fluctuation. As all things in experimental physics happens, there's some randomness going on that you can't account for. And okay, you if there's a diagram here, try to draw it. So yeah, your energy as a function of your gate voltage, so this is your energy, this is gate voltage, looks something like a bunch of like intersecting quadratics. And it's technically like self-similar across the whole thing. So we don't have to actually look at the entire spectrum to get what's going on. We can just restrict ourselves to like one like segment of this parameter space. So for this purpose, we just picked ng to be between 0 and 1. I could be wrong, but this is kind of similar to like the Berlin zone idea in condensed matter physics, if you did that. Okay, now the actual question, so for part A, what we want to know is if we assume that the gate voltage is uniformly distributed on like this 0-1 interval, then we want to find what's the probability density of the ground state energy. So U is defined as your ground state energy in units of this charge energy, the EC. So yeah, we basically just want to find the probability distribution. So you probably remember from the first lecture. So if you have 2 probability density functions, so say like P of x dx, that's equal to normalized to 1, and another one that's P of y, some other function, P prime of y, dy. These 2 can be related to each other because they're both equal to 1 as been like well-behaved normalized probability distributions. And you can go from one to the other, like kind of similarly to like a change of variables in math. So you like connect them by Jacobian. So we're interested in finding what's the Jacobian or the absolute value of it and apply it to this case. I'll rub some of these out because you don't really need this background knowledge stuff. Okay, so to look for this Jacobian, what we first look at is that, okay, we're interested in the interval ng between 0 and 1. But as we said before, ng being less than a half and ng being larger than a half gives us two different ground state energies. So ng less than a half, ground state corresponds to n equals 1, n equals 0, I'm getting that wrong. So our ground state energy U is equal to EGS divided by EC, and that's equal to 4 times EC times NG, times NG squared, and 4 EC NG squared divided by EC. So these two cancel out. So all we have for the ground state U for n less than a half is just equal to 4 NGS, NG squared. And for the ng larger than a half, where n equals 1 is the ground state, then U is equal to 4 times 1 minus ng squared. So we got two separate cases that we're to consider. Eventually you realize that they're actually exactly the same, but like, let's just do it one by one and convince us of that. So let's do the first case where ng is less than a half. So U equals 4 ng squared. And we want to find this Jacobian of dx dy. In this case, our x could be U and y could be ng. So let's do du dng. Basically, the derivatives are just switching between two variables. So this equals a ng. And we can invert this expression to get ng as a function of u, so then we can have this as just like a expression in terms of u instead in terms of ng, because we want to switch all the way to the u variable. So from here you can see ng is equal to square root of u on 2 by just inverting this expression. So then putting that in here, we find du dng is equal to 4 root u. Yep, so that means if we follow the lecture notes where your probability distribution in the new variable is given by the probability distribution in the old variable divided by the Jacobian, du dng, that's an absolute value. Then this becomes pretty easy. It would just be the old distribution is just a uniform distribution 1 divided by the new the Jacobian we just worked out here. So just 1 over 4 root u. So this is for ng between 0 and half piece. Okay, so now let's look at what happened in the ng between a half and 1 piece. So we do the exact same thing, except this time u is equal to 4 1 minus ng squared. Okay, so let's see, what do I do? Okay, du dng is still fairly easy. So this is minus 8 1 minus ng. Okay, but in this case, when we want to invert the function ng in terms of function of u, there are two options. So we can either get ng is equal to 1 minus root 2 root u over 2, or we can get ng is equal to 1 plus root u over 2, depending on which sign you take when you take the square root. So let's try both out because it's like either or. So for the first case, then putting that in, we get minus 8 times 1 minus 1 plus root u over 2.
then these two, the ones cancel out, so I end up with minus 4 root u, which is exactly the same as that, if after you take the absolute value. Or with the other case, or du dng is equal to minus 8, 1 minus 1 minus root u on 2. The ones cancel out again, but the minus sign cancel out, so it equals 4 root u. So when you take the absolute value, it doesn't really matter what you take. These two give you the same answer. And the probability distribution for this piece is, again, 1 divided by 4 root u. So these contribute identically between ng is less than 1, larger than a half, or ng is larger than 0, less than a half. And so what that means is that the entire probability distribution, you have two contributions that are identical. So the overall contribution just then like doubled. So overall, P prime of u is equal to 1 over 2 root u. So this is the total contribution. Yeah, all good. Okay, so one more thing to check. Okay, technically, if you do it this way, you can kind of be assured that the normalization is like kind of preserved, but it's always good to just double check. It's also a good way to make sure that you're actually doing the whole thing correctly. If your normalization's off, you probably miscalculated somewhere. So check normalization is easy. So we just check, does this integrate back to 1? So 1 over 2 root u du. So, oh god, doing integrals by hand. This is u to the 3/2. No, 1/2. 2 between 0 and 1. Okay, so that's 1/2 of 2 minus 0. So that's equal to 1. So we're all good. It's the normalizations are fine. So that tells us the rest of it should be okay. Okay, and now that we have the distribution function P of u, or P dash of u, then for part B, we can start taking moments and find what the like high order statistics are. So what's the first one we want to find? I think it's average. Yeah, find a mean. So we want to find, oh, sorry, we're going to plot it first. So the plot. So if this is P dash of u, and this is u between 0 and 1, this should just go to infinity at 0 and then approaches 1/2 at 1. So we'll just come down like that. I'll plot it on Wolfram Alpha. It's probably prettier than my drawing. But yeah, okay. Okay, so for part B, first finding a mean. So the mean of u will be just integrating u weighted by the probability distribution function du between 0 and 1. So that's equal to 1/2 integral 0 and 1 square root of u du. And that is 1/2 u to the 3/2 2/3 between 0 and 1. So that's 1/2 of 2/3 minus 0. So equals 1/3. So it means 1/3 kind of makes sense because it's like heavily skewed towards the 0 side. So most of the weight will be over here. So your average wouldn't be like near the middle as you would with a uniform distribution. Okay, and the second one is the standard deviation. But standard deviation you need to find from sigma squared. So sigma squared is the average of u squared minus square of the average of u. So we got this already, that's 1/3. So we just have to find this piece. So to find average of u squared,
integral 0 and 1, 1/2 u to the 3/2 du. So that's equal to 1/2 u to the 5/2 2/5 0 to 1. So that's equal to 1/2 2/5 minus 0 equals 1/5. So okay, now sigma squared is then u squared minus square of the u. So that's 1/2 minus, oh not 1/2, 1/5 minus 1/9. And I can't do math. 4/45. Okay, and the standard deviation is just sigma, not sigma squared. So you just take the square root of that. So standard deviation of this is approximately 0.298. Yeah, very simple stuff. Okay, so for the next part, you go to another energy limit, but at this point, the only thing that's changed is that your ground state energy is now in terms of something else. Is that too high? Your ground state energy, EGS, is now given by some factor W on 2, 1 minus cosine of 2 pi ng. Okay. And now we do the exact same thing. We want to find the probability of U, given that the probability of ng is still uniformly distributed on 0, 0 and 1. Okay, so now our U is still being defined similarly, except this time is EGS, instead of divided by EC, is divided by W. So we don't actually need to know what the W is. Apparently it's something physical if you're interested. So U is equal to 1/2 1 minus cos 2 pi ng. So take the derivative. Du dng is equal to minus, no, not minus. Derivative of cos is minus sign, so the minus signs cancel out. So we just get 1/2 2 pi sine of 2 pi ng. The pi's, the 2's cancel out, so we just get pi sine 2 pi ng. And now we have to invert this expression to find ng as a function of n, u. So, okay, if I look at the first expression, 2u is equal to 1 minus cos of 2 pi ng. So cos of 2 pi ng is equal to 2u, 1 minus 2u. So then ng is equal to 1 over 2 pi arc cos of 1 minus 2u. So we put this inside there. So then this equals, what was it? Pi sine of inverse cos of 1 minus 2u. If you look that on Wolfram alpha, it equals pi square root of 1 minus 2u squared. Okay, so now that we got Jacobian, we can just
take it to the relationship. So P prime of U is just 1 divided by Jacobian, so 1 divided by pi of square root 1 minus 2u squared. Okay, so for this one, we didn't have the same problem as we had before, where ng kind of made the ground state energy like into 2 separate pieces. You see confused, is that all right? No? Okay, that's all good. So yeah, in this case, ng is technically like defined for on this entire interval. But if you look at a cos graph, then on this interval, I think there's a plot of it. It looks something like this. Okay, this is meant to be the same height. And 0 and 1 is 0 and 1 is between these 2 dotted lines. So 0 and 1 is this piece. And the problem with this is that this function is not onto. So you have 2 x values that gives you the exact same y value. So you again can't exactly do this Jacobian trick like naively. You have to again cut it out in half, because it only works on bijective functions. So you do it first for the first half between ng is between 0 and 1/2. And then you just say, okay, by symmetry, these two like exactly the same gradient. They just go into the opposite direction. And since with this trick, you take the absolute value of the derivative, you're gonna get the exact same answer when doing over here. So once again, this is just gonna be doubling the first contribution. So you just pick up an extra factor of 2 on top. So you just could be careful when your function is like not obviously bijective. So it always helps to draw it out to just make sure that you don't have any weirdness going on. Okay. So we can make this look a little bit prettier if we just do some simplifications. So you can expand this out and you eventually cancel out a couple of prefactors, and you should hopefully get pi times square root of u minus u squared. Okay, so again, check for normalization. Just make sure that we did it correctly. So integrate 1 over pi square root of u minus u squared du. I was once upon a time able to do this in 4-unit, but it's been a while, so I used Mathematica, and it told me it was 1, so you have to believe me as well. Okay, I did get the symbolic answer, so it was minus 2 on pi inverse sine of square root of 1 minus u between 0 and 1. Yeah, so 1, that's 0, so that's 0 minus, minus 1, so minus pi, so this is equal to pi on 2, so this is equal to minus 2 on pi, 0 minus pi on 2, so equals 1. No idea if he's going to make you do these on top of your head in an exam. I hope, hopefully not. Okay. So yeah, we have to find the moments for this. Okay, so again, the average, okay, I'll write that out. So P dash U is 1 on pi root U minus U squared. I definitely use Mathematica for all of these because no way I'm doing these by hand. 1 on pi U on square root of U minus U squared. And that was 1/2. Oh, if I drew it out, maybe it would like make more sense why it's 1/2. So U P prime of U. In this case, at U equals 1, 0, it looks like this. So it's symmetric. So that's why the average will land right at half, as it should.
And then find u squared. 0 to 1, 1 on pi, u squared on square root of u minus u squared, du. And that equals to 3/8. So then your sigma squared is 3/8 minus a quarter. So it's equal to about 0.354.
Yeah, all good. For the next part, it's just kind of qualitative. Suppose we somehow could reduce the random contribution to the offset charges. So instead of being uniformly distributed, it was instead Gaussian with a variance, sigma squared. So I have some variance, eta, as much less than 1. And where would be the best place to park the qubit to minimize dephasing? That's what value of Ng set by the gate voltage will we find the smallest fluctuation on the ground state energy. So, okay, if you get through all of this condensed matter language, what it's basically asking is where will be the smallest standard deviation. And standard deviation, if you think about it on a Gaussian, it's just the width of the Gaussian. So the width is 2 sigma. So if you can find a peak that's really, really skinny, then the width will be very small. So then your 2 sigma will be very, very small. And then your sigma will be very small. So the goal of the game is to find a very sharp peak. And the peak, if you think about the way we define the probability distribution, P prime U is equal to 1 over, P of Ng. Let's not assume Ng is uniformly distributed anymore. Du dNg. Then you can see as the derivative kind of goes to 0, as this vanishes, your distribution goes to infinity, so it becomes like infinitely sharp, like steep. So if you can find somewhere where your ground state energy is like flat, so if like a plateau where this derivative vanishes, then you will be able to get a very, very sharp peak, or at least like a very like kind of steep angle at there, and the standard deviation around there will be extremely small. So you will have like the smallest, like minimizing dephasing is what they call it. So yeah, that's all you have to say. There's not much actual calculation to do. All good? No questions? Okay, so then question 2, another Stirling approximation question. So it's basically asking for the validity of the approximation. You have the full version where log of n factorial is approximately n log n minus n plus half log 2 pi n. And then you can have an even lazier version where you have log of n prime, m factorial is just n log n minus n. And the question is, at what point, how big does n have to be for this to be valid? So, okay, this is like mainly a plotting exercise. So if you plot out all 3 terms in the first expression, so this will be like the size, and this is n. Then plotting out n log n versus this half log 2 pi n, then you'll see the graph looks somewhat similar. So n log n looks like this. I should have made it steeper because n is meant to be like diagonal. N log n is like that, and then n is pretty much diagonal, and the other one's tiny. So half log of 2 pi n. Okay, so you don't want to be comparing this to the n log n term, because the n log n term is obviously the dominant term. The question is always going to be, how small does this have to be compared to something else before we can start ignoring it? So let's just say that like 1% threshold. So if we say if half log of 2 pi n is 1% of n log n, then we start ignoring it. Then you could run into the issue where, like, say somewhere like around here, for example, let's say here, where n log n is equal to 200, your n is equal to about like, I can't tell how much is on my drawing. It's about 100-ish. So 1% of that will be 20, so it'll be like here. And you can see, if you start ignoring at 1% of n log n, you still have this quite sizable contribution compared to n. So if you're ignoring it at that point, then you could run into the fact that these two terms added together will be significantly different to this term. So you should be comparing to the least dominant contribution. So if this term becomes 1% of the next least dominant term in the expression, then at that point we can say ignoring it, we wouldn't notice in the scope of things, in the scheme of things. So, okay, then the question's, okay, we want 1/2 log of 2 pi n to be smaller than 1% of n. So how big n does have to be? We just solve for half log of 2 pi n is equal to 0.01 n. I don't think there's an easy way to solve this. It's a Lambert function, Lambert W function. But you can very easily do it in Mathematica. So if you just put this in Mathematica, then it tells you that n is approximately, I think it was 390. So once n gets past 390, you can ignore this term up to 1% error. And if you want to do a bit better, you can also do like 0.1% of n. Then all you have to do is just add another 0, so this is equal to 0.001 n. And going through the same thing, but n doesn't scale linearly in this case. To ignore at 0.1%, you have to go up to n of 5,197 for it to be a subdominant contribution. Yeah, I think that's all you have to do for this question. Look, honestly, it sounds funny, but like ever since they started doing take-home exams, I think some classes actually allow it now. So you never know. But I don't know if it's a good news for you or not, because if they allow things like Mathematica and textbooks, the exam is going to be a lot harder. Yeah. But yeah, it's like one of those things. If you're doing tutorial problems and you're like, there's no way I can do this by hand, chances are you're not going to run into it in the exam. Yeah. Okay. That's it for this week. We could go. So tutorial 5, I kind of didn't go through a lot of it because most of it is kind of like discussion questions. They're kind of interesting to think about as food for thought. But there's like very little calculation to do, and some of it is kind of ambiguous enough that there's really no definitive answer yet. So, but I think I could go through 2 of them that I think are relatively standard. Okay, tutorial 5.
So this is back to tutorial 5. There was
Question 6 that I didn't do last time. So question 6 asks, demonstrate that for a paramagnetic system to reach absolute zero, a mathematical diversion around heat would need to flow from system to environment. So the way they do cooling for magnetic systems
via like two processes. So it's like a sequence of adiabatic and isothermal.
It's pretty interesting to read up. So the way they kind of like adiabatically demagnetize something or magnetize something, and then remove the external magnetic field, and then let the magnetic domain realign itself or like scramble itself, and that process costs work, and that extracts heat. And then you do that repeatedly until you get it to a lower and lower temperature.
But what that means is that on a TS diagram, you can actually visually kind of see what's going on. So on a TS diagram, if you have two magnetization curves, so let's say this is the low magnetization and this is a high magnetization, and you do like this adiabatic magnetization and demagnetization process, you kind of going like between adiabatic, isothermal and adiabatic, and then isothermal, and then adiabatic, like that. And mathematically can show that this process, although it looks like it's approaching like lower T quite quickly, it actually takes like an infinite number of steps. So, okay, you have your Curie's law, and you have your expression for dq in the magnetic system, so du minus VH dm. And then you can write out du's Vm dH minus VH dm, plus VH dm minus VH dm. So these two cancel each other out, and you end up with dq is just equal to Vm dH. Okay, and then your Q is just integral of going from the initial magnetization to the final magnetic field of V and then sub M for the CH on T dH. So that equals VC on T of HF squared minus HI squared. So it depends on the difference between the two magnetizations. But as you can see, this is the amount of heat that you have to pump out to achieve this difference in magnetization. Then as T approaches zero, as T goes to zero, then this goes to infinity. So at lower T, to change between the two field lines, it will cost you like progressively more heat until you couldn't do it anymore. Okay, and question 7 is that I can't remember. Maybe I did this last week. I can't remember. 2 weeks ago. Question 7. Derive the Gibbs-Helmholtz equation. dG on T divided by dt at constant P is equal to minus H on T squared. Okay, so your normal Gibbs function, minus S dt plus V dp. So if you divide it by T and then find dG on T then would just be to do this like not with this expression, but like in general, if you just pretend these are two like agnostic mathematical symbols, then just a quotient rule. So t dg minus g dt on t squared. Okay, and the final thing is that g, the Gibbs function, is just the enthalpy performed with one extra Legendre transform to replace the t and s variables. So now put equation 1 and equation 3 into equation 2 for the right hand side. Then you get dg on t is equal to minus g plus ts divided by t squared dt plus v on t dp. And then using this as a the enthalpy definition, you get a minus h on t squared dt plus v on t dp. Okay, and then you also say, okay, if I again look at this completely pure, like as a mathematical expression, then it's technically dg on t dt holding p constant dt plus dg on t dp holding t constant. And then you have a dt, dp, dt, dp. You just compare the coefficients. So I don't care about the dp one. So the dt coefficients, you get this is equal to that, which is what we're trying to prove. So it's always the same trick. It's like you write down all these like expressions that you know, and then you plug them into, simplify them down to some form that looks familiar. And then you compare this to like a general mathematical way of writing it down and then compare coefficients. A lot of these questions like that. And okay, just for fun, you can do question 8 as well to get the enthalpy. So yeah, for ideal gas, we'll find the enthalpy. Question 8. So for an ideal gas, the internal energy is F on 2 nkt, and the ideal gas law equals nkt. So then for the first one, you can say that's okay, F on 2 PV. And the enthalpy, you know, is the Legendre transform the internal energy, where you want to get rid of the like swap the P and V parameters around, variables around. So it's U plus PV. And so dH is equal to du plus dPV together. I'm not going to expand that out for now because I have an expression for PV. I can just put this nkt directly in here. I don't want to like mess around. Okay, so U is this, and I'll just have to find du. N, K, and F, they're all constants for an ideal gas. So this is just equal to F on 2 nk dt plus dPV is the same as d nkt, and again nk is constant, so just nk dt. Okay, so then collect the like terms. I get F plus 2 on 2 nk dt, and that's my dH. So then I just have to integrate that to get the enthalpy.
H is then equal some integration constant, H naught, and some initial enthalpy, plus F plus 2 onto NKT. And this is your heat capacity, if you recognize that. So yeah, and then you can play this exact same game to keep going to get the Helmholtz free energy and Gibbs free energy, but I won't bother with that here. Yeah?
So why wouldn't we just be able to put in U and EV straight into the enthalpy equation? Why do we need to integrate it first? Oh, sorry, derive it first.
You can put it into here.
Yeah, because we've got a function for U, we've got a function for VV, so why do we need to derive it first before putting it in?
Yeah, true, there's probably no point. But like, the process for ideal gas is probably very simple, but then if you have something more complicated, it might not be immediately applicable.
Maybe just a H0.
Yeah, you'll miss out on that term, true. Yeah, I don't know, honestly. I don't know when this will not work. I don't know if this is like the safer way, but yeah, you're right. In this case, you can just plug it in. Yvonne Wong used to say, with thermodynamics, you just put it in and do partial derivatives until something physical looking comes out. Don't think too hard about the process. Okay, well then that's it for this week. I'll see you guys next week.